SN2 mechanism. There are two types of nucleophilic substitution, SN2 and SN1. SN2 means bimolecular nucleophilic substitution. It represents that the reaction involves two molecules, haloalkane and the nucleophile in the rate determining step. So that's SN2. 2 because it involves two molecules in the rate determining step, and it's called bimolecular nucleophilic substitution. For SN1, it's unimolecular nucleophilic substitution because the first step involves only one molecule, and the molecule is haloalkane. There is no nucleophile in the first step of SN1 mechanism. Only haloalkane, only one. So that's why the name is unimolecular nucleophilic substitution. For SN2 mechanism, primary haloalkanes undergo SN2 mechanism. So if you have haloalkane, the class is primary, so primary haloalkane will undergo SN2 mechanism, not SN1, SN2 mechanism. In SN2 mechanism, the process of bond breaking and bond forming occur simultaneously. It's one-step mechanism. SN2 is one-step mechanism where bond breaking and bond forming occur simultaneously, means break the bond and form the bond at the same time. The SN2 mechanism is a second-order kinetics. So rate equal to K concentration of haloalkane and concentration of nucleophile. So in SN2 mechanism, the rate determined by the concentration of haloalkane and nucleophile. For example, CH3Cl react with OH- as the nucleophile. This is the haloalkane, and the product is alcohol and Cl- as the leaving group. So the rate equal to K concentration of haloalkane times concentration of nucleophile OH-. So it means the rate depends on the concentration of both reactants, where the reactants are haloalkanes and nucleophile. You must take into account the concentration of both in SN2 mechanism. So that's why it is second order kinetics. In SN2 mechanism, it's only one step mechanism. It has a transition state, no carbocation rearrangement because there will be no formation of carbocation step because it's only one step mechanism. Bond breaking and bond forming occur at the same time. So there will be no carbocation formation first and then the nucleophilic attack at the carbocation. No, there will be no carbocation formation. So if no carbocation formation, no carbocation rearrangement. So the first step is nucleophile attacks the delta plus carbon in haloalkane because we know that halogen is more electronegative than carbon. So halogen delta minus, carbon delta plus. This makes a haloalkane carbon electrophilic site. So the nucleophile will attack carbon electrophilic site, means it use the lone pair, the nucleophile lone pair is used and forming a bond with carbon in haloalkane. This reaction is a slow reaction. Nucleophile attack C delta plus haloalkane is a slow reaction. The transition state is nucleophile is about to form a bond with carbon and the carbon-halogen bond is about to break. So this is called transition state. The first reaction is halogen leave this transition state is a fast reaction. So X minus as a leaving group leave C single bond nucleophile as the product. So from transition state to become the product is a fast reaction. From reactant to become transition state is a slow reaction. Example: all SN2 reactions proceed with backside attack, resulting in inversion of configuration at electrophilic carbon atom. So this is what we call backside attack. When you have halogen, this is carbon, and halogen on this side, on the right side or at the front side, the nucleophile will replace this halogen, but it proceeds with backside attack, so it won't approach this carbon from the same side as halogen. No, it will attack from the back. The nucleophile approaches for the side opposite of the leaving group. We know that the halogen is a leaving group on the right side, so the nucleophile will attack from the opposite side. Remember that the reactant to become transition state is a slow reaction, and from transition state to become the product is a fast reaction. Order of reactivity in SN2 mechanism. The higher the number of alkyl group in haloalkane, the lower the rate of SN2 reaction to happen. So for SN2 mechanism, it prefers lower number of alkyl group in haloalkane. This is because the backside of electrophilic carbon atom is hindered by the presence of bulky alkyl groups. So if the haloalkane has bigger number of alkyl group, means the haloalkane has more alkyl group, the backside of the electrophilic carbon atom is hindered by them. So if you compare this one, this is the backside because we have halogen in front, so we call it this side backside. This carbon has no alkyl group or HHH. If you compare with the haloalkane, which have all alkyl group 3, for example CH3, 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 bigger size than HHH, so more number of alkyl group hinder the attack of nucleophile from the back, means it makes the nucleophile difficult to attack the electrophilic carbon because it is hindered by the number of alkyl group here. So the higher the number of alkyl group, it is less likely for the SN2 reaction to happen. So this is a primary haloalkane because the halogen attached to primary carbon. This is secondary haloalkene, tertiary haloalkene. So tertiary alkyl halides or tertiary haloalkenes are more hindered, this one, more hindered than the secondary haloalkene. Secondary haloalkenes are more hindered than primary haloalkene. So primary haloalkene prefer SN2 mechanism if you compare to tertiary haloalkene.